Here in Geneva. Good afternoon, everybody in Melbourne. Jeff, can you hear me? Okay, I just wanted to greet Jeff Taylor, who is over there and chairing the meeting over there, and we will come back to you with questions at the end of the second talk. There will be no questions after the first talk, questions only after the second talk for both talks together. Okay, I think today is a special day. I'm diplomatic. Today is a special day in several senses. I think, that, at least to my knowledge, this is the first international conference on high energy physics which is opened via video conference on a different continent. That shows that we are a global community and that we are working and talking to each other globally. I think that's very important to point out. So, today is also a special day because we hear two presentations from the two experiments, Atlas and CMS, on their update on a search for a certain particle. I forgot the name. I'm sure the experiments will remind me on that. Okay, I don't want to make too many words. Today we are starting in the non-alphabetical order, and I ask Joe Incandela from CMS to take the floor.
Okay. So I have to look up there, huh? Can you go full screen? Okay. So I will give the status of the CMS Figs Church. What I want to say, well, there's a lot to say, actually. And so it took quite a bit of effort to compress all the work of really thousands of people over many years into the small number, I think 175 slides, that I show here. And, so it's very tricky. But one of the big stories of this year was, as you know, those of you in the field, is pileup. We had to deal with very intense beams, like never before seen in the field, with many, many interactions. And this slide shows you one event taken just a few weeks ago. The colors correspond to tracks from different particles. And then if you look along the other view, you see all of the vertices that are involved. And this event has estimated 50 interactions, 14 jets above 40 GeV, more than 2 TeV of uncorrected energy. And it was in these kind of events that we're looking for one of the rarest particles ever made. So keeping that in mind, this is a very, very preliminary result, but we think it's very strong, it's very solid. Otherwise, we wouldn't present it. On the other hand, I see all of my young experts who helped me prepare the slides, and many, many people went many days without sleep, including me, but I slept last night, so that was a first. And lucky. I want to really dedicate this to the CMS collaboration. It's a fantastic collaboration. This is a picture we took last week. We had a party. This is only 400 or 500 people. Remember, there are 4,000 people in the experiment. This is not the real CMS detector. That's down underground. This is the spare that we keep upstairs. Okay, so one page for the theorist. That's all they deserve. No, I'm kidding. The standard model is here, is shown here. This is what we know. These are the particles making up the standard model that we've known and seen up till now. The amazing thing is that it's been tested for years and years at LEP and so forth. And we have now confirmed it to better than a percent in really hundreds of measurements. It's getting really quite annoying, but very impressive. I mean, it's just amazing. But there's one piece that's missing, and that's what we call the Higgs. And that's what we're going to talk about today. And so this is where things stood last week. Let's see if this works. Yeah, okay. This is where we stood last week. As you know, if you look at the radiative corrections to the W, there's a connection to the top, goes like the top squared, to the Higgs that goes like the log. So if you know the W and top mass very well, you can actually predict along bands where you would find the Higgs. And there were two major developments last year. One at the Tevatron, they really had a tour de force measurement of the W mass down to 15 MeV, which is just astounding for a Hadron Collider. And that shrunk this ellipse. I'm kind of nervous for some reason, I'm not sure. Shrunk this ellipse down to this green one. And then the colliders, this whole space here was gray. And you can see, in 1 year, we basically eliminated a 475 GeV band of possibilities. And we were down to just this spot. And you see they nicely intersect there, and that's a good place to look. And that's what the rest of this talk will be about. Now, we moved to ATeV this year. So here's the cross-section for production of standard model Higgs. Mainly, it's direct production via gluon fusion through a top quark loop. But there are many other ways it can be produced. One that's very important is vector boson fusion, and that will come into play here. But in fact, all of the four main modes are exploited in our searches, including TTH, which I'll show only very briefly, but it will be discussed more at ICHEP. An important thing about the ATeV is that we gained relative to 7TeV last year by about 25 to 30% in the rate of production of Higgs at low mass. So this is very important, and you see that in the data and the results. Actually, I can use this thing. So where do we look? In this talk, I'll talk about 5 decay modes. These are the branching ratios of the Higgs. If you're at high mass, it's mainly vector bosons, but we're looking in this little range that I told you about, and it's a very interesting range because it has a rich array of decays. So it's fantastic from the physics standpoint. From the experimental standpoint of trying to find this, it makes life harder because you have many things that it's splitting to, and you have to try to dig them all out. So for the low mass searches, which I'll concentrate on today, we look for BB bar, tau tau, WW, ZZ, and 2 photons. And we get very good mass resolution in these 2 channels. So the region that's not yet excluded is about 115 to 130, let's say. I mentioned the 5 decay modes, and this shows our sensitivity to setting limits or excluding the standard model in these 5 modes. And you can see in this range, we're actually fairly comparable across all of them, within a factor of 2 or so. They're very, very strong now, these modes. And then this combines them. And so the one thing you know, of course, you have no idea what I'm going to say at the conclusion, I know, but the one thing you know for sure is that we are in a position to exclude the standard model at this point. Looked at it another way, you can ask, what's the discovery potential? Now, the probability that the background would fluctuate up to a given signal, the size of the standard model, given where we are now, is shown for the 5 channels here, and this is the sum. So in this range, we'd expect somewhere between 5 and 6 standard deviations excess if there was a standard model Higgs. And we'd have excellent opportunities, we hope, with more data to really study this thing. Okay. How did we get here so fast? One of the key ingredients was the LHC. I want to thank Steve and all of the people involved, Lynn, who put this amazing machine together and ran it. You can see this is the 2010 run down here. That's not a mistake. That's actually the first year of running. It was there last year, and then this is the rocket we're on right now in 2012. So in this talk, we use about 5.2 inverse femtobarns from 2012. And this 5.2 inverse femtobarns is perfect. So we collected actually 6.7. We're still working on gathering more data. It takes some time to certify data that has slight problems, but already 5.2 is golden. 5.6 is good for any kind of a muon analysis as well. And so those are the samples we used this year. Last year, they're just slightly smaller in size, but they're at 7 TeV. This is CMS. I can't spend a lot of time. I could spend hours on this, but there's some key things about CMS. This is a detector, I think, that has built on many generations of experience. From the Tevatron, we learned that silicon works well in tracking, and we gambled in CMS and built an all-silicon tracker. That's 200 square meters of silicon, almost 10 million channels. Inside of that, there's a 66 million channel pixel detector. Outside that, we have all of our calorimetry inside of this amazing magnet, which is 3.8 Tesla. It's huge stored energy, holds the entire tracking system in calorimetry, and gives us a fantastic effect in terms of being able to spread out all the particles coming out from the interaction. And this is effectively increasing your granularity, which is already very, very high in CMS. And that gives us a lot of power, and we're still learning what this detector can do. And it's still surprising us, I think, to some extent. The hadron calorimeter is brass scintillator and works very well. But the really exceptional thing is the electromagnetic calorimeter, which is another first for a hadron collider. It's made of lead tungstate crystals, about 75,000 crystals. Each is about 30 centimeters long, 2.5 centimeters around. So in principle, the Mollier radius is really within one of these crystals. You should be able to capture an electron. Of course, electrons won't hit dead on center face. So typically, an unconverted photon will be contained in 9 crystals, the one surrounding the hit and the one that is hit. And these are all crucial to our results I'll show today. I'm going to run over, Rolf. No, I'll try to pick up the pace. And then we have these muon detectors, which are very, very nice on the outside, completely hermetic and redundant. All right, everything's working great. I'm going to pick up the pace. This is 100%. You see everything's working very well, close to 100%. And this is amazing after 3 years of running that we can keep things going this well. It's taking more effort. People are getting tired, but it's going well. Now, the eCal is crucial to several of our measurements, Higgs 2 photons, all the electrons in ZZ and so forth. So I wanted to show you briefly some of the things we do. We use many low-energy, Etas, Pis, and so forth to get the low-end calibration, intercalibration. We also use W events. But with radiation, you see our response is falling. Radiation damage, the crystals are becoming less transparent. We monitor these with lasers. We have to do a correction that involves modeling how light propagates in the crystals. That's applied. That's the blue line. And you see it brings us up to here. So in WE new events, we actually have a 0.2% stability across the run. This takes a tremendous amount of effort and a lot of people involved, but it's done very well. And then we get very good resolution, as you can see here, at the percent level. Moving on, I just want to give another reason we got here is that last year we found, I don't have time to explain this slide in detail, but what we found, if you just listen to the words, is that with this high pileup of many interactions, the processing time per event went up dramatically, and we would not have been able to run this year very well. So our computing guys and many of the people in physics dug in and found a factor of 2.5, in speed, so that we were under about 15 seconds per event. And we were able to do this without changing any of the cuts, without actually having any cuts on tracking or anything. So that got us in very good position to take data this year. And our Monte Carlos. We produce about 400 million at generator level per month. That's a huge number, and 1 billion per month that are digied and reconstructed. So that's part of the reason we were able to show results this quickly. Okay, in terms of reconstruction, using the high granularity of the detector, we have what we call a global event description, or what was called before particle flow. It's based on particle flow. And the basic concept is you start with real physics, generally just basic particles. They get manifested in various ways in your detector. We combine all that information, we return a list of reconstructed particles, and basically reconstruct something very close to the original underlying interaction, the real interaction itself. And that allows us to do a fantastic job of doing the physics. Everything can be done from this list of particles, and it eliminates redundancy, simplifies isolation, and so forth. And you'll see some of the effects of that. For electrons, we have very sophisticated electron reconstruction in the eCal. We take into account, using Gaussian sum filters, the energy lost due to Bremsstrahlung. As you know, that's a stochastic effect. You can't just use a simple Gaussian. You have to actually mix Gaussians, and that's what's done in this. And that allows us to track out to right out to the eCal. And we have very specific photon identification, and for energy scale and resolution, we use Z's and J size to electrons, and we also study photons with Z's. And you can see then the comparison of data in Monte Carlo in the barrel is excellent. And we have about a 1.2 GeV resolution. For electron identification, we use multivariate techniques. We feed a lot of information, and we found a 30% improvement, in fact, in H to Z, Z to 4E this year. This has gotten us some improvement. And you can see the kind of separation we're getting between electrons from Z's. And these are actually additional jets in Z events that pass loose lepton requirements. And you see they fail our multivariate. And you see our working points here. This is signal efficiency versus background efficiency. This is where we were in 2012 for low PT, and now we're up here. And for high PT, we're up here. So we're gaining everywhere in sensitivity. I have to move more quickly. I'll just say that for muons, we also have particle flow muons. We get really high efficiency down to 5 GeV. Fantastic efficiency above 10 GeV. You can see this studying the J size and Z's. Remarkable how flat our efficiency is and how high. And this is the more remarkable thing, that there's completely no dependence on the number of interactions. And this has been taken out in the last few months. For isolation, we do something fairly sophisticated. I'll get into it later. But we sum the energy of the particle flow particles in basically in rings around the main particle. And again, we see that the efficiency of the isolation cut is completely flat. You can see now also here, this is for muons, you see for electrons how much better we're doing. This is efficiency, you can't see it. This is background, and we've gone from here to here. So we're higher efficiency with lower fake rates. Tau identification is very sophisticated. We actually reconstruct 1, 2, and 3 prong. We can reconstruct rows and A's, and we get incredibly high efficiency, as high as 70%, with a very low fake rate. And again, we use these for isolation. We use energy deposits in rings and feed that to a multivariate discriminator. For jets, we were quite worried. At the beginning of the year, the pileup adds lots of jets, and that changes your jet counting, which affects your categories for the different different Higgs searches. And what we've learned is that we can compensate by knowing, of course, what tracks are tracked from the tracker, where they are coming from what vertex. But even outside the tracker, we can see the jet shape is different. Typical pileup jets are often overlaps of just several different particles, and the structure is different. And so you can see this is our the ratio of jets to of the fraction of events with 0 jets in various bins of multi-interactions, and they all lie on top of each other. And here's the ratio with the lowest multi-interaction bin, and you see there's a couple of a % spread here, and then almost nothing. So we've eliminated the impact of pileup, basically, which I find just astounding. And with this kind of thing, and in general, this is 2011 plots. I didn't have time to get the new ones, but I wanted to say that we have fantastic jet resolution. This shows you jet PTs out to 1 or 2 TeV, within 15% of expectation at next to leading order, and a magnificent Joule-Yan spectrum, again, bang on, all the way out to 1.5 TeV. So, in summary, we understand, I didn't talk about top, but we understand top. We've got the top mass and reconstruction coming in very well, cross-section, and we've slowly, as we've gathered data, rediscovered the standard model to more and more rare processes, and basically we're very confident now that we can go after the rarest, which is the Higgs. So, I'll start with Higgs to 2 photons. This is a magnificent event, very clean, showing 2 photons and very little else, nothing centrally really. So we have a main analysis which is multivariate based on boosted decision trees. We have a multivariate for the photon ID, and then we use that to basically not tell us anything other than how to classify the events. We split the events into different classes in such a way that we maximize our ability to distinguish set limits or have sensitivity. And we end up with 4 event classes. And then with a low cut on the MVA output, we add 2 digit categories for sensitivity to vector boson fusion. We cross-check this with another model that has an alternate background model, extraction. And this is, I'm missing the name of it here. It's dropped. This is the sideband, right? So this is the sideband subtraction. It's another way of doing things that is inherently, it's complementary, but it doesn't use, for instance, the signal region in the fit for the background. And we wanted to make sure we have that unbiased. And then we have a very simple cut-based cross-check. And this is our previous publication. Even so, we've done very well in improving all of these things with the improvements we've had in the various objects that I mentioned already. This has had a big impact on our overall sensitivity. So this is a comparison of our data to Monte Carlo. The analysis was blind. All of our analyses were blind in 2012. In other words, we did not look at the signal regions. We developed all these new techniques optimize them without ever looking in the band where the signal would be, so that we can be very honest with ourselves, and also keep everyone calm, because if you're looking in the signal region, it gets a little wild. But it was very good, and people did a very, very good job. And you can see the comparison with, at least with Monte Carlo, of the different signals. But the background Monte Carlo is not used for anything. Oops. It's only used for optimization of the selection, okay? But we also use ZDE, for instance, for photon efficiencies, and all these things are mostly data-driven. Here you see the photon energy scale and resolution. We do clustering. Here's a very basic 5x5 crystal clustering distribution that you get for using to reconstruct electrons for a Z, and you see it doesn't work very well. You go to our basic supercluster definition, which allows some extension in phi, rather, for Bremsstrahlung, and you start picking up the low tails from picking up the Bremsstrahlung. And then we have a regression technique based on multivariate analysis that does a fantastic job of sharpening up the peak. And you can see here as well. There's one difference, one problem, though. In Monte Carlo, things are a little bit sharper. That's the pink. And so we do use also a multivariate technique to understand exactly what the resolution should be in many, many different partitionings of the detector location and so forth. And we apply those to resmear the Monte Carlo, and you get the black curve, and then you see the data on top of that. And they're just right on top of each other. So we think we have the modeling done very well. For photon, this is the photon pre-selection. I just want to point out that we select photons as a function of the mass of the diphoton system. And we make sure, well, these are technical things, but it's also MVA-based photon discrimination, and we get very good separation from fakes. And this is just showing the output of the multivariate discriminator. And you can see the signal, the Monte Carlo is in blue. The red bands actually give you the uncertainty, and then the data is right on top of that. And we invert the electron veto in ZDE to use those samples to validate these multivariate analyses. Okay. For mass reconstruction, it depends a lot on the vertex position. We have to get that right. At least the resolution does. You don't always have to have the right vertex, but having it helps. If you're off by more than a centimeter, then the position actually impacts the resolution more than the inherent instrumental resolution. So you want to be within a centimeter. And here you can see we do very well, about 83% correct in 2011. With pileup, we didn't lose much. We put lots of things into a boosted decision tree. This is also a multivariate technique to take into account what's happening at the vertex to see if the tracks are actually balancing the direction, the movement of the photons in the other direction, and so forth. And you can see our efficiency as a function of the PT of the gamma-gamma system. And this is checked on Z to mu mu, and you can see data in Monte Carlo match extremely well. All right, I think I'm finally close to getting to results. Last thing I want to say, I said this before, we use this multivariate analysis to actually split the events into categories in such a way that we get the best possible results in the end. We don't use the multivariate for anything else than splitting the events. We take the splits and we fit them, and we extract mass directly from the shape. It's just to give us the best splitting, to try and group different events with different resolutions together in a way that optimally obtains the best result. And so these are the various splits. This is background. This is what we expect for Higgs signal. And this is data. And these are the categories. And you can see the data is in the black, and the different colors show the different backgrounds contributing. And category 0 should have the least background, 1 the next, second, third. Each one gets a little bit more background, and you'll see in the plots are more and more events. And then we just discard this bit down here. It just doesn't contribute anything. Here's a nice candidate for vector boson fusion. You have a nice pair of photons and 2 very forward jets. We have 2 categories. The highest category, which has a higher boost required, we think would be, on signal samples, about 80% pure. VBF, vector boson fusion versus gluon fusion production. So this is a nice event. I won't go into the details. This shows you a little bit how we make the selection. There's a loose and a tight. As I said, the tight category gives you about 80% purity of VBF. This one gives you about 50%. By splitting in these categories, we gained about 15% in our sensitivity, which is very important. We also remove jets from pileup, as I've shown you before. We do lots of studies and cross-checks. So these are the results from 2011 data in the different categories. These are without the dijet tags for VBF. And you can see the signal that would be expected superimposed in all the different categories. and there's quite a bit of jitter. It's quite hard to see if there's really anything there. You can maybe see some little excesses here and there. The background model is entirely from the data, as I said. We fit to the mass distribution according to each category with third to fifth order polynomials. We choose based on getting the lowest bias. So the bias has to be no more than 20% of the statistical error in Monte Carlo. And then we keep it, that's the 20%. And this causes some loss of performance, but otherwise things go well. We also have this cross-check. This is, I'll show you very quickly the, did I switch? 2012 data. Again, 0, 1, 2 tags, 3 tags. Now you see the dijet tight and the dijet loose, the two new dijet categories. Again, it's quite hard to see if anything's there. So what we have done is combined all of these, weighting them by signal to background, which is how a discriminator would look at all this data to try and extract a signal. And when you do that, this is what you see. So that's fairly significant. Okay, and then if we look, it's hard to leave that. For me, I was lost for a moment, excuse me. So what we see then, if we look at what would be our exclusions, right, for 95% exclusion for cross-section relative to standard model Higgs, you see our expectation is this dashed line. We do pretty well in staying below it in many places, but we have an excess that's fairly substantial here at around 125 GeV. As you may recall, there was a little bump here last year as well, and I'll show you what's going on with that a little bit later. Maybe the next slide even. Yes, here it is. So what you see here is now the p-values. This is the probability that the background could fluctuate to this extent. And you see, combining the 2 years, we're beyond 4 sigma, about 4.1 standard deviations. And what's quite important to see is that the 2 years, the red is 8 TV data, the blue is 7 TV. They're both finding something here. And on the other hand, this bump that we saw in 2011 is not really reproduced, although there's a little one next door. So this, however, is kind of compelling. This shows the best fit to cross-section as a function of mass, and you see what the axis we see seems to be a bit more, about factor 1.5 or 1.6 times the standard model. If you look at all the different channels that we've presented in 7 and 8 TV, you see they're spread around this average. And it's about what you'd expect for the statistics, I think, if that was a true average. But with each of these individually, of course, you don't have much sensitivity. It's only in that combination that you saw that things become significant. Okay, moving on to Higgs to ZZ. Okay, obviously it's a very clean, narrow peak that we're looking for. Main backgrounds are ZZ star. Then there's reducible backgrounds, Z plus jets, where jets fake leptons. TT bar, of course, where the heavy flavors can have leptons. But then you have extra jets and other dibosons. It's one of the most strong performing channels in the whole mass range. But down in the low mass range, you can see the various things you could look for. We're looking in this analysis today. There will be other analyses presented at ICHEP with different decay modes. Here we're looking at the 4 lepton channels. So this is all the 4 lepton channels, where lepton, I mean E or mu, not tau. And you can see our sensitivity to all combined. This is electrons plus muons. This is electrons. And then we also have 4 muons. And this shows the PT of the 4 leptons. The dash would correspond, from Monte Carlo, of course, at 126 GeV, would correspond to what they would look like before all the selections and then what happens after all the selections. And this is our sensitivity. Everything was, again, analyzed and optimized blindly. We even applied it to our reoptimization in 2011. We did not look in this range or there. And I've already mentioned many of the new features. They're listed here. In the interest of time, I won't go through them. But we had about a 20% improvement at this mass range. And this shows you our expected exclusions. One of the things we've also done is now picked up final state radiation. We're using our particle flow again. Around the lepton, we look for a photon. It can be as low as 2 GeV if it's within a cone of 0.1. But if it's beyond that cone, it has to be, that cone size has to be above 4 GeV out to 0.5. And we also associate under these criteria, we want it to look very good. if we get closer to a Z. And you can see the impact it has in Monte Carlo on the distributions for 126 GeV. So we get a nice symmetric distribution now. We apply these. The irreducible backgrounds are modeled from data. Reducible backgrounds also estimated from data. And then we extrapolate from control regions. And let me show you now one other key thing. We look at the final state angles of the leptons. Now you have four particles, ignoring the masses, there's 3 degrees of freedom each. Once you allow for momentum and energy conservation, you're down to 9. Then there's a rotation, which is arbitrary in phi, so you have 8 final variables, and we go to a representation of the masses of the 2 Z's, the various angles, and the masses of the 4-lepton system. And we find that, for instance, in the mass of the 2Z, we get very good discrimination between background and signal, and many of these other variables as well give us some background discrimination. So then we can look at our data. This is a matrix element likelihood calculation that's done event by event. And I can show you, if you distribute what you'd expect for 126 GeV Higgs, what this discriminator value would be between 0 and 1 versus the 4-lepton mass. You'd expect an accumulation here. For all the backgrounds, it's rather well distributed. So you look here, this is another way of looking at it. Signal, background. Okay, these are some nice events. 2e to mu. This is 2e to mu with a photon that's been recovered. And again, with another photon that's been recovered. And here's the data. This is the full distribution. This is the zoomed low-end distribution. Now, what's quite nice is you see that we can pick up this rare process, Z gamma star radiating Z gamma star, produce a 4-lepton Z decay, and that produces a very nice peak that we model in Monte Carlo and match very well in data. And then as you go forward, you see that then there's some excess here. And what we're showing you is the distribution you'd expect for 126 GeV Higgs. And these are the event-by-event errors. If you go through the slides later, you can see all of the events that have been, what the expectations are. Now, this is the Mela distribution of the data. Remember, this is comparing to background. Remember, background is rather diffusely distributed. If I then compare it to signal, you see that there's something quite interesting here, that we have an excess events at this high end of this discriminant, which is not at all consistent with background. Now, there's something also very interesting to point out. If we look at MZ1 and MZ2, you can see the expectations in red for Higgs and then these other colors for the kind of continuum and reducible backgrounds. And you can see our distribution of events. And they tend to be rather broadly distributed in both cases. Something like this, whereas you'd expect a concentration here. You might worry that this is background, but it's even more unlikely for background to do this. So it's quite an interesting effect, and it's probably something we should consider just the result of low statistics at this point. But it's not something we'll watch. It's very interesting. Then, taking our original mass distribution, if we make a cut on this discriminant, background is really killed, and you see that there's still a hefty number of events in this region. So we're seeing something. It's relatively significant, and it's behaving like signal in many ways. And if we then look at what kind of limits we can place, this is looking over the full range. We can set 95% exclusions in many regions. A couple spots we can't. If you look at the p-values, well, our expected significance for standard model Higgs at 125.5 is 3.8 sigma, and what we're seeing is 3.2. So a lot of consistency with what one might expect, possibly being a little unlucky in the number of events that we got, if it's signal. And here I show the blow-up of these things. And you can see, again, the p-value, we would have expected to be a bit lower. There's an interesting shoulder here that we're studying, and there's a possible TT bar event there that may have had some impact. All right, so now we can look at the sensitivities. If we combine the ZZ and gamma-gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5 standard deviations. the last month of running that did it. So I just thank Steve for getting so much data the last month or so of running, because we are very close to that 5 sigma. It's nice to be at 5. Now the situation gets more complicated. We'll add some more channels. Okay, Higgs to WW. The basic idea, we're looking for the pure leptonic decays, E's or mu's. So the backgrounds are diboson, the irreducible ones. I'm sorry, this is direct production. This is actually signal. You have a very large branching ratio. You expect them to be the leptons to be close in delta phi as compared to backgrounds. The backgrounds are W continuum, top, other backgrounds. So the signature is 2 high T leptons and large missing T, which is fairly clean, but not so simple because there are many. We're looking for very, very rare events still. So the backgrounds, which you might think are not so bad, are difficult. The strategy is purely data-driven. We use W plus jets. For the W plus jets, we get a fake rate from QCD. We normalize Z gamma star to the Z mass, and we do various ways of understanding how it would be affecting us at high end. For top, we can use B tagging. We try to keep the jet count low to avoid top, but we do use 0, 1, and a VBF category, which is dijets. And we look at all the different combinations of lepton flavors. So far, we only have the cut-based approach ready. Our most sensitive analysis is a multivariate one, but it's not ready. So we'll hopefully in the next weeks or months show you even more powerful results here, but the cut-based was very solid. I won't go through all of the thousands of histograms that are required to study this channel and just jump basically toward the end. You see the data, you see our expectations for the background, and this is before the final 2 most sensitive cuts, which is the delta phi between the leptons and the mass of the dileptons. And we're looking in the 0 jet and 1 jet bin here. And you can see this is where we cut away. We throw that out, but we get pretty good matching between, in any case, statistics are low. And then this is what we keep, that we feed down to these, and then we cut this end out. And you can see there is a little bit of an excess. In this case, the 1 jet, maybe not so much. And this is what we would expect for our ability to set limits on standard model cross-sections. We should be able to exclude this region between the dashed lines, which is fairly broad. And in fact, this is what we see. There's a slight excess here. This is how it's distributed across these various things. It's a little bit below what you'd expect for standard model, about 0.6. We did get also got some improvements of order 5% here. Now what I wanted to show you, let's see if I have it. I think, no, yes. So I can only show you this for ATV. We didn't get a chance to do the full combination. Again, this is the signal. This is our observed. Could be signal observed plot. This is the expectation. We wanted to see what would happen if we had 125 JeV Higgs. So we did many toy models and injected it, ran it through, and I will now show you what it would look like. And it's pretty striking. That's what it would look like, and this is what we have. So it seems to be reasonably consistent, but of course these are low statistics in early days. Okay, I have 2 more channels which have limited sensitivity, but that we finished that are interesting to look at. I have 10 minutes. I'll make it, I think. BB bar. Okay, this has a huge cross-section, but we can't get at it from the background, so we're forced to look at associated production, W or Z to Higgs with Higgs to BB bar. We dig this thing out of a huge background, and these are the various channels we look at down here in this range here. So we're looking at associated production of W and H and Z and H. I think I should move this down, actually. I'll fix that later. So we have 5 channels we look at depending on the leptons, and then there are various reducible backgrounds, QCD, top, WZ plus light jets. Less reducible, of course, are vector bosons plus Bs. We use the boost of the vector boson system and 2 very well-tagged Bs. Require these things to be back-to-back, and we reconstruct the mass. Here you can see the PT boson distribution for Zs for various sources. The red is the Higgs. You see it's a bit broader. So we get some discrimination there. We also do a very nice regression technique to get better resolution on the BB bar mass. And we've improved very much from last year, about 50% sensitivity overall. And here's a nice candidate. You have 2 B jets, 2 mu's. These are the final distributions that we look at. In some of the cases, there are actually many more that I can't show you, but these are just examples. Z to EE plus BB bar, W mu nu plus BB bar, Z nu nu plus BB bar in the ATV data. And you can see that things are pretty close to what you'd expect. And this is what we get for the limits. So it's compatible with 125 Jev Higgs. Now if you add the significance of the W's, we're at 5.1 sigma. Expected 5.2. Last, we look at Higgs to tau tau in these 4 channels. This is also a greatly improved analysis. Has very high signal to branching ratio at low end. Sensitive to all production modes. Has good coupling to leptons, obviously. We can look for MSSM in this channel, but it has very challenging large background. So a lot of work had to be done to try to understand this. What we do is actually we break the events up into 5 categories. And as I said, we look at these 4 states. We have 5 categories based on mass resolution, signal to background. We fit all 5 simultaneously. There's a low, 0-jet, low PT bin that's very high in background. And in the fit, this helps us constrain the background overall. Then there's a 1-jet, low PT that gives you an enhancement from the single jet. There's a 0-jet, high PT that gives you enhancement from the high PT. And there's a combination of these 2 that gives you even a more, jumping to the results, don't want to do that. Even more enhancement. And then we also have a VBF category where we look for jets, 2 extra jets, and no jets in a rapidity gap, and this is MVA-based selection. We do a very fancy fit that I'm not going to explain in detail, but it gives us a very good reconstruction at the correct masses. This is a Z, and this would be a Higgs at 120 Jev. So this gives us about a 20% improved resolution over 2011. So much to our surprise, this channel became quite sensitive already this year, and I'll show that. So these are some examples of the final distributions. This is E mu, 0-jet, E tau, 1-jet, mu tau in the VBF category. And of course, we have all of these different ones, plus mu mu in all 3 of these categories, but I can't show you them all. But you can see they're different. This one, as I said, it constrains backgrounds, energy scales, and I'm sorry, this is the energy scales and efficiencies. This is not the low PTN. The 1-jet is an enhancement to gluon fusion. And over here we have this rapidity gap and dijet case that we look for impacts of possible VBF production. So this is our sensitivity last year, relative cross-section relative to standard model for a limit. And this is what we got this year. We're just above standard model, you can see. So this was a big surprise to us, but it was a tremendous, really tour de force effort. So this is what we see. No evidence of anything really at 125, and we come close to excluding the standard model at 125. So we were wondering what would happen if you inject signal, and so this is what would be the case. So this is quite an interesting channel, but before we get too excited, there's very few events involved, and we can trace where this comes from. There's a deficit in a bin that's probably driving this at the level of a few events, so it'll be very interesting to see what happens. But this also shows you we're really at the beginning. This is very low statistics. We have a lot of work to do. We need to run a lot to finish this up. All right, so let me go through the full results. So I have 5 minutes? Perfect. So these are our sensitivities for the full range and the blow up of the low mass range. As I said, we should be able to exclude the standard model pretty much everywhere. If it was not there. And this is what we see. Obviously, we have an excess here that you've already seen. This is the signal strength that we see. Again, at about 125. And then, I've already shown these. These are the 2 high sensitivity channels. This is adding the W. Now, if we add the other 2 channels, we fall below 5 sigma to 4.9 sigma. And we appear to be, we would have expected 5.9, so we appear to be about a sigma below where our expectations are, which is not dramatic yet. We'll have to see how things go with more data. This shows, I'm sorry, I was trying to remember with it. This shows the 7 TV data and the 8 TV data again, which are very consistent in this region. And if you do a likelihood scan for mass, this is something that just came out in the last day or two, so we've added it. I didn't expect this to be ready. You find all the results are consistent from the high-resolution channels, Higgs gamma gamma, untagged, VBF, ZZ, and the combination sits about right here. And we looked if we can fit for the mass. This shows the different channels, and the black shows the combination, and we get 125.3 plus or minus 0.6 for the moment, which we'll hope to improve upon. So, to summarize, at this point at least, we've observed a state decaying to diphotons and 4 leptons with statistical significance of 5 sigma. It has a mass around 125. So next we want to look at some of the characteristics. Of course, what can we see for compatibility with the standard model of Higgs, but keeping in mind, of course, this is very early and very low statistics. But it's showing we're just setting up to do some of these measurements. And with more data, they should become more interesting. So again, compatibility with the signal strength. Our overall best fit is 0.8, but they're consistent in 7 and 8 TeV samples. Not significant. This shows the distribution across the various channels and subchannels, the scatter around that 0.8. This is 7 and 8 TeV data combined. Now we go to a little bit tighter combinations. These are the 5 channels I showed you and how they distribute. And this is showing the 4 different production modes. So untagged, VBF tagged, associated production, and then TT bar Higgs, which I won't go into, but a result will be presented at ICHEP. And we're getting some sensitivity there, better than we had expected as well. So everything is pretty much self-consistent across the topologies, but it's very early. Keep that in mind. What we looked at too was how well the W and ZZ channels are performing relative to each other, because you expect custodial symmetry, and you find, in fact, that the ratio is 0.9 with large errors. So it's consistent. And then we looked at the couplings themselves in a scan of the vector boson coupling and the fermion coupling. This also just came out, I think, last night, so it's very early. And it's pretty much in agreement with the standard model at 95% confidence level. Standard model's here, this is what we're measuring. So it's a bit off, but again, we need more data. Okay, so to wrap up, in summary, we've seen this, we calculate this, we lose the page number, and we conclude by saying that we have observed a new boson with a mass of 125.3 plus or minus 0.6 GeV at 4.9 standard deviations. Thank you. One minute. I wanted to show a few, can I show a few acknowledgements? Thank you. Thank you on behalf of CMS. I wanted to acknowledge a few people. First of all, there were many things that have been done by the theoretical community and standard model predictions that have been just spot on over the years. It's a tribute to a huge amount of work done for all the accelerators by many theorists. We thank also the Higgs cross-section working group, and of course, the 5 gentlemen, six, who contributed to the theory. This is actually to electroweak theory itself and electroweak symmetry breaking and Higgs theory. Thanks also to all the people involved in the accelerator groups, all of the DGs who have been involved. It took 6 DGs to get here, actually, which is pretty amazing. It's an incredible project. I'll let you read this on its own. Here's a picture of all the spokesmen I think are in here from all the experiments over the years. And again, CMS collaboration, who worked like crazy to get these results done in this time, which is, I think, a phenomenal record, considering we stopped taking data 2 weeks ago. So I thank them all. Hope they all sleep well tonight. These are all of the institutes in CMS. We have 3,300 scientists. I'd like to thank. I'm almost done. Thanks to all of our funding agencies. And I also wanted to say one last thing. I would like to thank the member states of CERN. I can say this. I'm not from a member state, but I think it's extraordinary that they have opened CERN up and these projects to all countries in the world. And that's a magnificent thing, because these results are now global and shared by all of mankind, I think. So I thank you for that. Thank you. Okay?
We'll leave the mic on.
Okay.
Okay, I think I can only say congratulations to everybody. I will say a few words more later. Now we go immediately to Atlas Fabiola Gianotti, please.
Thank you. So, good morning. Atlas is very pleased to present here today updated results on standard model X searches based on up to 10.7 inverse femtobarn of data recorded in 2011 and 2012. And it's a big honor and a big emotion for me to represent this fantastic collaboration at this occasion. So you can see here some beautiful events selected by our X search. So are these really X candidates? Well, I start to have some doubt, because recently I learned from a Swiss-German newspaper that this is how the Higgs boson could look. It's not quite the same thing. And from what I've seen from CMS and Joe, CMS also is not on the right track. So by the way, this object is quite scary. So more seriously, we present today updated results on standard model X searches based on the data recorded in 2011 up to 4.9 inverse femtobarn and 2012 up to 5.9 inverse femtobarn at 8 TeV. Results are preliminary. In particular, the 2012 data are very fresh. They've been recorded until a couple of weeks ago, with harsher conditions than in 2011 due to the larger pileup, up to a factor of 2. As Joe already said, pileup is the number of simultaneous interactions per branch crossing, and because we have deployed for the first time new improved analysis. So for these reasons, we present today updated results with the 2012 data for the two high-resolution channels, X2 gamma gamma and X2 4 lepton, which are the most solid channels. They have a high sensitivity in the low mass region. They are expected to give rise to narrow signal peak, mass peak, and they are minimally sensitive to pileup. Other low mass channels, which were shown before by Joe, contains missing energy in the final state. So they are less robust against pileup. They have a poorer mass resolution. In some cases, you can't see a mass peak. And they suffer from a complex mixture of backgrounds. So the understanding of the detector performance and the backgrounds for these channels were advanced, but the results are not mature enough to be presented today. So when presenting you the full combination, this low mass resolution channel will be injected with the 2011 result, 2011 data only. So this plot shows the integrated luminosity recorded by Atlas in 2012 as a function of time until essentially now, so until the June technical stop. We have recorded 6.3 inverse femtobarn, corresponding to a data taking efficiency of 94.6%, with a fraction of non-operating channels at the level of a few per mil in most cases, which I think is a remarkable achievement for such a complex detector, which was conceived 20 years ago, built 10 years ago, and has been operating already for 3 years. Also high is the good quality data fraction, that is the fraction of data that are certified to be used in the analysis, is at the level of 93.6%. So when you put everything together, 90% of the delivered luminosity is used to produce these results, goes into the plot. This fraction is slightly larger than last year, in spite of the very fresh data and despite of the harsher conditions. So I think this is a great achievement of the collaboration and the results of a huge amount of work. So this plot, similar version was shown already by, I should stop saying that Joe has said this and that. It's really, it's not easy to speak second because all the clever things have been already said. Anyway, so this plot, this plot shows the impressive progression of the delivered luminosity as a function of time over the 3 years, 2010, which is essentially underflow, 2011 and 2012. I think I don't have to make any comment, just big thanks to the whole LHC exploitation team, including the operation, the technical and infrastructure group, and to all the people who have contributed to the conception, design, construction, and operation of this superb instrument. So, thanks a lot. The price to pay for this outstanding performance of the machine and the high luminosity is PILUP. PILUP is the challenge in 2012. As you can see from this plot, which shows the interaction, number of interactions per crossing as a function of time. And you see that today we are operating at the level of 30 interactions per crossing at the beginning of the field, which is larger than the 23 per crossing, which is the experiment design value. So we are working above design, beyond design, and it was expected to be achieved only with a luminosity of 10 to the 34, so not so quickly, not so fast, and of course this is the reason why we are there already now with this high PILUP is because the bunch spacing is twice larger than expected. So here you see one of these spectacular events. It is due to the production of a Z boson going into two muons, which has been produced in association with many soft interactions, and we reconstruct an additional 24 vertices in these events. So over the last months, we have invested a lot of time and efforts to prepare the experiments to work. Oops, sorry. No, it's right, yes. To work in these conditions and to mitigate the impact of PILUP on the trigger, on the reconstruction of the physics objects, and on the physics resources. So we have developed PILUP robust fast algorithms, and we have optimized the reconstruction and identification of physics objects, electrons, photons, muons, jets, missing ET, etc., in order to maintain it at the same level, or even better in some cases, as with zero PILUP condition, and also to keep it constant with a number of interactions per crossing, and I will tell you later on why. And we've also refined the modeling of the PILUP in all its components, in time and out of time PILUP, which is quite complex. I will show an example later on, in our simulation. This is one example of this, the results of this painstaking work. As you know, missing ET is an important handle for low mass X searches, but is also one of the most sensitive variables to PILUP because it integrates over the full energy in the calorimeter, which with large PILUP is subject to enormous fluctuation. And so you can see that indeed ET-miss is very sensitive to PILUP. Here, in this plot, we show the ET-miss resolution for Z to mu events as a function of the number of reconstructed primary vertices, which is a quantity proportional to the number of interactions per crossing. And you can see the dramatic deterioration of the missing ET resolution. But then, if you apply PILUP suppression algorithm, for instance, based on the tracking information, but not only, then you can bring the resolution down at a very good level, and also you can also notice that it's stable as a function of PILUP. Not also the very good agreement between data and Monte Carlo, which testifies to the good understanding of the simulation for this very delicate issue. So I would like to spend 1 minute on trigger, because at the Hadron Collider, operating in these unprecedented conditions in terms of luminosity and PILUP, the performance of the trigger is challenging. When the luminosity goes up, of course, it's very easy to raise the threshold. By raising the threshold, you kill physics, especially you kill low-mass objects like the Higgs boson. And results from the 2012 operation show that our trigger is coping very well with the harsh condition while capturing the interesting physics. And in particular, we have been able to develop PILUP robust and fast algorithms. CPU is very important, in particular at trigger level, and to optimize the selection, for instance, introducing isolation, so that we are able to keep threshold for inclusive, unprescaled inclusive leptons at a very relatively low level, at the level of 24 GeV or so, which is very important for physics, in particular for X searches, and die lepton threshold at the level of 13 GeV or so. And note that over the last 2 years, the luminosity has increased by almost 2 orders of magnitude, and our lepton threshold have only changed by 5 GeV or so. So this is also the results of a long optimization work. Of course, our trigger menu is not just this simple table. It contains 500 items, but I don't want to go into all the details of that. So I will just show you one example of the trigger performance, because this is the first crucial element in the whole chain. Here you can see the efficiency, trigger efficiency for the inclusive electron trigger down to a threshold of 24 GeV as a function of a pileup, as obtained at level 1, at level 2, and the event filter. These are the 3 trigger levels in Atlas, and you can notice 2 things. First of all, the efficiency is extremely high, 94%, and is stable with pileup, is pileup independent. This is very important because the machine today has found an operation point, which is very good, by which when they inject beams and the beams are stable and are good, then the field is extremely long, several hours, and that allowed us to record a lot of luminosity. But of course, the pileup along the fields changes from 30 at the beginning to 10 at the end. So clearly, if your selection, if your trigger, if your offline criteria are pileup dependent, then first of all, the analysis becomes a nightmare, and also the control of the systematics becomes very difficult. So it's important, very important, to have stable performance at all levels as a function of pileup. I would like to briefly mention computing, because it will be impossible to present physics results today based on a huge amount of data and so quickly, less than 2 weeks since the start of data taking for this data, without the outstanding performance of the worldwide grid, including high rate first pass data processing at the tier 0, massive Monte Carlo production at all sites scattered all over the world, more than 80 sites, and worldwide analysis. And actually, the people who have contributed to the analysis that I will show here, many of which are young people, I'm very proud of this, are located at institutes from all over the world. So I will now move to physics, and before moving to Higgs, one plot to summarize the present measurement of cross-section in Atlas, electroweak and top cross-section, including W and Z, TT bar, single top, including first observation of WT production, and dye boson, WW, WZ, and ZZ, using 2011 and 2012 data. This plot is very nice because it shows that the standard model works well at 7 and 8 TeV with some little tension here and there that I will mention later on. But this measurement, of course, they are important on their own, but they are also a necessary foundation for Higgs searches. And the reason is that many of these processes are reducible or irreducible background to Higgs searches, so they have to be known and mastered very well. So I will not spend any time on the Higgs production mechanism and decay modes in the interesting, the most sensitive channels in the interesting mass range, because Joe has described this already. But I want to draw your attention to one thing. I've tried to summarize in 3 lines what is the impact of the center of mass energy on Higgs searches, because sometimes this is not very clear. So the Higgs cross-section increases by typically 30% for a mass of 125 GeV when going from 7 to 8 TeV. The several irreducible backgrounds, like gamma-gamma and dye bosons, have a similar increase at the level of 1.2, 1.25. Reducible backgrounds like TT bar and ZBB bar grows faster with center of mass energy. So if you put everything together, the expected increase in sensitivity for a standard model Higgs boson this year, from the fact that we are running at 8 TeV, is at the level of 10 to 15%. And you will see this reflected in our results. So what is the status of Atlas Higgs searches until this morning? So this will last 5 minutes. So this is the usual plot showing the ratio between the excluded 95% confidence level by Atlas cross-section divided by the expected Higgs standard model cross-section as a function of mass. The points are the experimental results. The dashed line is the expectation in the absence of a signal, with the 1 sigma and 2 sigma bands in green and yellow, respectively. And you have seen that until now, until this morning, we have excluded essentially the full mass range up to 540 GeV or so, except a little island here and a window here between 122 and 129 GeV. That, as you see from the expectation tell us that we do have the power to exclude it, but we don't exclude it because we observe an excess. So to quantify the excess, the usual p-value plot, already shown before, which quantify the consistency of the data with the background only expectation. So if you are below 1 sigma, you are fully consistent with the background at the 1 sigma level. If you are beyond that, you have a different level of consistency. So you can see that the largest deviation is observed for a Higgs mass of 126 GeV. It is at the level of 3 sigma, and this is how the excess shares among the various channels. It is driven by X2 gamma gamma and X2 for leptons, while X2 WW doesn't bring much. When you look at the probability for such an excess to appear anywhere in the investigated mass region, the so-called look elsewhere effect, this significance goes, the probability is at the level of 10% of this effect. So although this observation is in good agreement with that expected from the standard model, it's also very well compatible with the background. So it's not really conclusive. So what's new in the result presented today? So first of all, we have propagated the experience that we have gained in 2011 in terms of detailed understanding of the detector performance, calibration, alignment, pile-up, extensive comparison between data and simulation, to the improvement of the reconstruction and identification of physics objects. And this has resulted in a sizable gain in efficiency, and we will see the impact also on the searches for the Higgs, in the minimization of the pile-up dependence and on smaller systematic uncertainty. Second, we have optimized the sensitivity of our X2 gamma gamma and 4-lepton analysis using the following procedure. The optimization has been done on Monte Carlo simulation only. Then we have looked at the 2012 data outside the signal region, so in the signal sidebands or in the so-called background control regions. We have extensively validated our simulation with the data and compared with the data in this region, and we have expected the signal region only after these two steps were accomplished successfully. This improved analysis have also been applied to the 2011 data, so I will show you here updated X2 gamma gamma and 4-lepton results also at 7 TeV based on this improved analysis. So in conclusion, well, before going to the meat of the presentation, here I will present updated X2 gamma gamma and 4-lepton results with the full statistics data recorded at 7 TeV and 8 TeV for a total of almost 11 inverse femtobar, and a new overall combination where the other channels are based on the 2011 results. So let's start with X2 gamma gamma. This is relatively simple final states with two high PT isolated photons, and a signal is expected to appear as a narrow peak on top of a huge background, which is smooth and is dominated by the gamma-gamma continuum. So to increase the sensitivity of the analysis, we have divided the data sample in 10 categories, depending on whether on the rapidity of the photon, central or rest, whether it's converted or unconverted, on the PT of the diphoton system. The main improvements in the new analysis is that we have introduced a two-jet category addressing in particular the vector boson fusion process, which is expected to give rise to two jets mainly in the forward region. And we have improved the photon identification, in particular using a neural network for the 2011 data. So these improvements, we expect that these improvements bring a gain sensitivity at the level of 15% compared to the old analysis. Now, it looks simple. However, note that the signal-to-background ratio for this channel is extremely small. After all the selection cuts, photon identification, etc., in 11 inverse femtobar of data and in a mass window around 126 GeV, we expect something like 170 signal events from a standard model Higgs for a background of more than 6,000. So you see the signal-to-background ratio is very small. And therefore, the crucial experimental aspects for this channel in order to observe a possible sigma are an excellent mass resolution in order to be able to extract an arrow peak on top of this huge background, and also a powerful photon identification in order to suppress the gamma jet and jet-jet background with one or both jet faking photons, which is potentially much larger than the reducible gamma-gamma background and can be a killer for this channel. So we need very good photon identification. And I will discuss these two items one by one. First of all, starting from the mass resolution obviously receive contribution from the energy resolution for the photons and from the photon opening angle. Okay? So let's start from the energy. This table here, this box, summarizes the present understanding of the calorimeter energy response as obtained from data, Z2E, W2E nu, and GPSI2E. The energy scale is known to 3 per mil at mz. The linearity is better than 1% in the relevant energy range, and the constant term of the energy resolution, which reflects the uniformity of the calorimeter response, is at the level of 1% everywhere except in the transition region between the barrel and the end cap, where we need to do a bit more work. This is just one example of this performance. What you can see here is the stability of the response of the electromagnetic calorimeter as a function of time in 2011 during the full run, 7 months from March to October, as obtained from data, ZZ and W EDU. These two lines represent plus or minus 1 per mil, and the RMS of the points is at the level of half a per mil. So you can see how well we control, how stable is the calorimeter, and how well we control the response. So all these elements enter in the mass resolution for a possible Higgs signal, and so this is what the simulation gives us for the mass resolution of a Higgs boson of mass 125 GeV. The mass resolution for the inclusive sample is 1.6 GeV with very small amount of tails outside the mass region, which is also important. But the other thing that you can notice in this plot is that the mass resolution is essentially not affected by pileup. The various points refer to different values of pileup from essentially 0 up to the condition that we have today. And the reason why the mass resolution is so little affected from pileup is that we do not depend on tracking for the reconstruction of the photon angle, which is the second contribution to the mass resolution. So if you want to measure the photon angle, you need to know the position of the vertex. Okay? But this, of course, is not easy when you have the pileup of many events overlapping simultaneously in the same bunch, and because the LHC beam spot size is not point-like, it's not a point in Z, it has a spread of typically 5 to 6 per centimeter. So for this reason, when we conceived the electromagnetic calorimeter, we decided to segment it longitudinally. Well, this is not the only reason, but anyway, it's one of the reasons for segmenting it longitudinally in 3 compartments, which allows us to measure the photon direction, and by extrapolating back to the beam line, to reconstruct the position of the primary vertex. And the resolution of this measure is shown here, as obtained from a sample of gamma-gamma events. And you can see that the vertex spread that we have, from the measurement of the vertex from the 2 photons is 1.5 centimeters, which is a factor of 3 or 4 better than the LHC intrinsic beam spread, so that the contribution of the vertex resolution to the mass resolution is totally negligible. But also you can see how this is stable with pileup, because the 2 data points, set of points, refer to two completely different pileup situations. I mentioned the importance of rejecting the jet background. So this was one of the reasons for segmenting the first compartment of the electromagnetic calorimeter in narrow strips, 4 millimeter in the eta direction, to be able to separate a shower, single shower, coming from an isolated photon from the overlapping showers coming from the decay of the pi zero. And with this handle and many others, we are able to reject the jets at the level of 10 to the 4 for a very high photon efficiency, 90%. And so if you now take our gamma-gamma samples after all cuts and we perform a data-driven decomposition of the sample, we indeed see that 75 to 80% of the events are real gamma-gamma, and that the contamination of fakes coming from gamma-jet and jet-jet is below 30%. So this means mission accomplished in the rejection of this background. Now, I would like to spend 1 minute to discuss one point which is perhaps a bit detailed for this seminar, but I think it's very good to give an idea of the subtle effects that we had to face when running in this challenging condition. So a rejection of 2 against jets is provided by photon isolation. That is, requirement that the energy in a cone around the photon is below a few GeV. The problem is that pile-up contributes to this energy. And for reasons that it will be too long to explain, this contribution of pile-ups depends on the position of the bunch inside the train. So if you don't correct precisely for this energy, then you see in your photon isolation energy a structure which reproduces very well the LHC bunch train with the field bunch, the small gaps, the big gaps, so we can really check if the guys in the CCC are doing the right thing with injection of the beam. So then, of course, we correct for this effect. It will be too long to go into details, but just to give you an idea of the very detailed work that we had to do to gain few percent in efficiency to reduce the systematic, etc. So I'm now going to the results for this channel. This is the final diphoton mass spectrum after all selection cuts. You can see here the distribution of the data. The data are fit with a signal shape, crystal ball plus a Gaussian, and a background model which has been optimized with Monte Carlo to minimize any bias and while retaining statistical power. Here you can see the data after subtraction of the background. You can perhaps notice some strange things going on here. I will try to quantify this excess immediately. Just mention that in the extraction of the results, we have taken into account a huge number of systematic uncertainties that have been carefully evaluated. So you see the background is determined from the data, from the fit to the sidebands, and is not based on any theoretical prediction. So let's go to the results for this channel, starting first in terms of exclusion in cross-section and in mass. You can see here the results for the 2011 to 2012 and the combination of the two. And here you can see how the exclusion changes with time. Essentially what we managed to do with more statistics is to essentially dump and consolidate, say, the exclusion in the side bands of the excess by dumping some fluctuation that he had in the past. Okay? Now, let's now quantify the excess using the usual p-value plot, showing the consistencies between data and Monte Carlo, shown here in blue for the 2011 data, in red for the 2012 data, and in black for their combination. The points indicate the impact of the small uncertainty on the jet energy scale at the level of 0.6%, which has an impact of 0.1 sigma on the p-value. So you see that in both here, with two statistically independent samples, we observe similar significances locally at the level of 3.4 to 3.5 sigma, whereas the expectation from the standard model is almost a factor of 2 smaller, as you see also from the combination, 4.5 sigma. Note that the expectation from a standard model Higgs increases in 2012 compared to 2010 because of the little increase in luminosity and so the increase in luminosity and the center of mass energy. When you include the look elsewhere effect, this significance of 4.5 sigma goes down to 3.6 sigma. So because the significance observed in the data is a factor of 2 larger than in the standard model, we expect that if you fit the signal strength in the data, the best value of the fit, which is shown here as a function of the Higgs mass, normalized to the expected strength for a standard model Higgs boson is larger, and actually the value is 1.9 plus or minus 0.5. So the preferred value is twice as large as the standard model Higgs boson expectation. We have an excess on the signal, but of course compatible with the standard model Higgs expectation within 2 sigma. And this plot is a consistency check showing the same mu parameter, the same strength for each one of the categories in which we divide our sample. And you see the results are very consistent. Let's now move to X24 leptons. So this channel has a tiny rate, very small cross-section. The mass can be fully reconstructed, as in X2 gamma gamma, from the final states product. However, unless in X2 gamma gamma, this channel has the advantage that it's very pure, because the signal to background ratio is 1, it's not 3%, is larger. So a handful of events clustered around a given mass will be extremely convincing. So we require in the final states 4 leptons with PT between 20 and 6 GeV. We also apply cuts on the leading and subleading mass of the lepton pairs. And I note that the main backgrounds are the reducible ZZ production. And in the low mass region also reducible background are important, like ZBB bar, Z plus jet and TT bar, with 2 leptons as real leptons and 2 fake or leptons from B decays coming from B jets or light quark jet. These backgrounds are suppressed by using isolation and impact parameter cuts. So the crucial experimental aspects for this channel is because the signal is very tiny, one has to have a very high acceptance and very high efficiency for the individual leptons, down to very low PT, because you see that a light object that goes in 4 leptons in the final states. And also good control of the reducible background, which can rely only on Monte Carlo because of the huge theoretical and experimental uncertainties, and so we have to evaluate by using control regions in the data. We have improved substantially this analysis over the last months. The main improvements are summarized here. We have optimized, in most cases, relaxed the kinematic cuts to increase the signal sensitivity at low mass. And we have increased dramatically the electron reconstruction and identification efficiency at low PT. So the total gain in sensitivity compared to the previous analysis is between 20 and 30%. And I will now spend 1 minute to illustrate in particular these improvements in the electron reconstruction, because this really made a difference. So high efficiency for low PT electrons is crucial for X24 electron and X22 muon and 2 electrons, though challenging because low PT electrons are affected by the material they traverse in the tracker before reaching the calorimeter. So we have improved our track reconstruction and fitting procedure to recover electrons undergoing hard BREM, and you can see the results of this work in these 2 plots, which shows the electron reconstruction efficiency as a function of eta and PT obtained from data, Z2E data and Monte Carlo, in red for the 2011 data, the old algorithm, and in blue for the new algorithm and the 2012 data. And you can see that at large rapidity, small PT with the material effects are largest, we gain between 5 and 10%. So the total reconstruction efficiency is 98%, essentially flat with PT and data, and also pile up. Second point, we have reoptimized the electron identification selection by using pile-up robust variable based on transition radiation in the TRT, in the strips in the calorimeter. And you can see here that the efficiency as a function of pile-up for 3 different set of selection, loose, medium, and tight, you can see how the flat is the efficiency reached in this way. Note also the excellent agreement between data and Monte Carlo, which testifies to the very good understanding of the detector performance and the sophistication achieved in the simulation to take into account all the subtle effects. So the total gain in acceptance time efficiency for X24 electron, including this improvement plus the improved kinematic cuts, is at the level of 60%. Compared to the previous analysis. What I gave you before was the sensitivity, this is acceptance on the signal. Muons are reconstructed in Atlas with an efficiency of 97%, flat in PT down to 6 GeV, and over a large rapidity coverage, 5.4 units. Thanks to the improvement of the analysis, in particular the new kinematic cuts, the total acceptance times efficiency has gone up by 45% compared to last year. This plot shows the expected mass spectrum for a Higgs going to 4 muon from the simulation, obviously, and you can see that the resolution is 1.7 GeV when using Z-mass constraint. The peak position is a few per mil from the real value of the mass. So the question is very good performance. The question is the simulation reliable? Yes, of course, it's reliable because we have tested it with objects that we can measure with high statistic like Z2 mu. And you can see that with 2 million muons from the 2012 data, the spectrum for data in Monte Carlo is extremely good agreement because in the Monte Carlo we have propagated all what we know from the data. And so this gives confidence that the simulation is solid. So let's move to the result. This is the reconstructed X24 lepton mass spectrum that you obtain by combining the 2011 and 2012 data, so almost 10.7 inverse femtobarn, all flavors together for E, for mu, to E to mu. The data points are shown by the data points. The Monte Carlo is shown in red, for the irreducible ZZ, and in purple for the reducible background. And you can also see the signal expected at for various possible X or various masses. So let's first look at the high mass region above 160 GeV, which is dominated by ZZ production. So here we observe 190 events, and we expect 147. So you see the observation, we have an excess. The observation is 30% larger than what we expect, in agreement with our measurement of the ZZ cross-section that we have performed also at ATV, and which is shown here as a function of center of mass energy compared to previous measurement at the Tevatron or in Atlas. And you can see that our data point at ATV is at 1.5 sigma or so, 20-30% larger than the next to leading order standard model prediction. In general, we have some excess in the data in dye boson compared to the prediction, so there is some work still to be done with our friends theorists. But anyway, the impact of this excess on the low mass region has been checked carefully, and it's totally negligible. Then we look at the low mass region. Okay, so below 100 GeV, and here we observe a peak at 90 GeV. Coming from the single resonant process. It was already shown by Joe, but actually this observation was pioneered by CMS. And this, because the lepton pairs here are particularly soft, this signal, say, can be enhanced by relaxing the cut, which we did, and then we find very good agreement with Monte Carlo in data. And this is again another sanity check of the reconstruction, muon reconstruction at low PT, and of the consistency between Monte Carlo and data. So I'm sure that you are curious now to look at the region between 100 and 160 GeV. And here we go. 2011, 2012, 2011 plus 2012 data. So in the region below 160 GeV, we observed 39 events with an expectation of 34 plus or minus 3. So good compatibility. Now, if you look at the region 125 plus or minus 5 GeV, which is above plus or minus 2 sigma, the resolution of a possible signal there, then you see that we observe in the data 13 events in total. Here, there are 13 data points in this mass bin. We expect 5 from background only, and another 5 from a signal of that mass. Here you can see the sharing among the various flavor final states, which also gives you an idea of the different purity of these final states. For muons is extremely pure, with a signal-to-background ratio of 1.6. For electron is the less pure, and also for muon is very little affected by the reducible background, whereas the other two channels suffer also from a reducible background, which is comparable with the reducible background. We have determined the reducible background using control region in the data. I don't have to go into details. I hope you trust me. If you don't trust me, in any case, I will go on the same. Only 7 minutes. Oh my God. Okay. 7 minutes, flexible. I'm sure you will not stop me before the last conclusion slide. Okay, so I show you quickly 3 gorgeous candidates. This is a 4 muon candidates, 2 muons in the central region, 2 muons in the forward region. Total mass of the 4 muon pair, 125.1 GeV. The leading pair has a mass of 86 GeV, the sub-leading 32 GeV. You see 15 reconstructed vertices in these events, one of which has produced the 4 muon pair. Next one, 4 electrons, X to 4 electrons with invariant mass, candidate 4 electron, not X. 4 electron candidate with mass 124.6 GeV, with all the electrons in the barrel region, very well reconstructed, and again, the activity of the event with 11 additional vertices, and finally a 2E to 2 mu event In this case, everybody is in the forward region, electrons and muons. Okay? So we see that we exploit the full power of the detector over the full acceptance. So, results for this channel, again, 2011, 2012, and the combination. And here are the exclusion. So what you see is that with more data, we are able to exclude more and more in the high mass region. This is not a surprise, because this region is already excluded. But at 130 GeV, we are stuck. We are against a wall. With more data, we are not able to go down in the exclusion. And the reason is that, of course, we have an excess. And the excess is quantified here through the usual p-value for the 2011 data in blue, 2012 in red, and for their combination in black. The excess of 2.3 sigma observed in 2011 is confirmed or even enhanced in the 2012 data for a total significance of 3.4 sigma, where we expect 2.6 sigma from the standard model Higgs. So again, slightly higher than the expectation, less dramatic than in the gamma-gamma case. And if we fit, again, the best strength for the signal at 125 GeV, which is the mass where we have the maximum deviation, we find a new value of 1.3 plus or minus 0.6 compared to the standard model Higgs boson expectation. Now, the grand combination. The channels that you have seen before, together with the other channels from the 2011 results. So, again, starting with the cross-section and exclusion. This is the situation up to now, this morning. In red, you can see the region excluded until this morning. And this is what we have now. Total blackout everywhere, except in this mass window here, between 122.6 and 129.7 GeV. And also note that a large part of this region is also excluded at the 99% confidence level. Okay? Of course, we don't reach the have sensitivity beyond 600 GeV, so I'm not talking about high mass region. I'm concentrating more in the mass region. So, quantification of the excess. This slide shows, again, the usual p-value as a function of mass, and also the significance now as a function of mass. I show the full mass range because it shows you the excellent consistency everywhere between background only scenario and the data at the level, fluctuation at the level of below plus or minus 2 sigma. So this distribution is extremely clean, except one big spike here, in this region here. So, zooming in this region. I'm not done yet. There is more to come. Be patient. I thought that's a good No. Wait a moment. So you can see that we observe an excess of 5.0 sigma. Actually, the plot shows 5.1. The reason is that the plot does not contain the impact of this energy scale systematics, which, as I mentioned before, gives a 0.1 sigma difference. So 5.0, when we take everything into account, just with these two channels, X2 gamma gamma and X2 4 leptons, and with the old channels for the old results for the other channels, which corresponds to a probability of background fluctuation, up fluctuation of 3 times 10 to the minus 7. And an expected significance from a standard model Higgs boson of 4.6 sigma. So you can already see here the compatibility between what you observe and what we expect from a standard model Higgs boson. Note also that the excess is here, 126.5 GeV. So clearly, from this compatibility, we know that now if we fit the signal, the best single strength in the data, we will find something very compatible with the standard model expectation, 1.2 plus or minus 0.3. So, one slide to discuss a bit the consistency of the global picture. I'm at the end, just 2 slides and 4 slides. I'm sorry, please. So what is the consistency between these results? We observe an excess in X2 for lepton and gamma-gamma. You may remember that the maximum of the excess was at 125 GeV for 4 leptons, at 126.5 GeV for gamma-gamma. What is the consistency? So we have made a two-dimensional likelihood fit to the mass and the signal strength for X2 gamma-gamma and X2 for leptons, and these are the results. You can see here the curves, which shows approximately 68% and 95% contours, and I don't have to spend much time to convince you that there is compatibility at this level of fluctuation and statistics. Remember, X2 for leptons, a few candidates, 2 candidates can make the difference, okay, between the various measurements. And here, again, fitting the signal strengths to all channels we have measured until now, look until now, you can see BB bar and tau tau are very large uncertainty. WW is consistent with everything. Gamma-gamma is a factor of 2 from the standard model, but with an error between 2 sigma, and then the combined value is exactly 1.2. Okay, I'm at the end. Just one slide to show the evolution of the excess with time. This was the p-value that you have showed at the EPS conference in July, exactly 1 year ago. You may remember we had both Atlas and CMS, remember we had a broad excess at the level of 2.5 sigma, dominated driven by X2WW. Then, at the time of the seminar at CERN in December for the council, we got something more serious, say, a significance at the level of 3.5. You see a narrower dip in the p-value because X2 gamma-gamma has a better resolution, of course, than X2WW. Then in spring, we also updated WW searches, and the significance went up again, deteriorated by 0.5 sigma. So X2WW fluctuated up and down. And finally, today. The next steps. 2 minutes. So the next steps are Atlas plans to submit a paper based on the data presented today at the end of July. Simultaneously with CMS, we are going to publish together and in the same journal. And in this paper, we'll add also the X2WW channel. More data. We need more data. Surprise, surprise. I'm looking at the NHT team. To establish observation in more channels, to look at a more exclusive topology, so we need statistics, and to start to understand the nature and properties of the new particle. And I'm very happy that we are entering now the very appealing era of X measurement. And of course, the first question is the observed excess to the production of a standard model X boson. The strength is similar, but we have to make sure that the sharing among channels is the expected one. So I would like to make a couple of notes. First of all, we have only recorded 1/3 of the data expected in 2012. So, sorry, what did I do? This is just the beginning. There is more to come. Second, the LHC and experiments have been doing miracles. I think that we are working beyond design, we are working beyond expectation. We have produced a lot of data and a lot of results much faster. So, please, in particular, theorists, be patient. Don't ask us if it's standard or not, how many, etc. Just there is a long path to go. So, conclusions. We have presented preliminary results on searches for a standard model X boson using the full data sample recorded so far for X2 gamma-gamma and X2 for leptons, and the 2011 results for the other channels. I think these results represent an impressive accomplishment of the experiment in all its components. I would like just to mention that less than 1 week after we recorded the latest data, so on the 25th of July, first plot containing the full statistics of the 2012 data, first results on X searches were already available, with a fraction of good quality data certified at the level of 90% of the delivered luminosity. So for me, this is an impressive, remarkable achievement of the dedication and highly skilled work of the collaboration. We have looked for a standard model X boson over the mass region 110 to 600 GeV in 12 channels. We have excluded a 99% confidence level, the region up to 523 GeV, except a window. And in that window, we observe an excess with a local significance of 5.0 sigma at a mass of 126.5 GeV. The excess is driven by X2 gamma gamma into 4 leptons, is in agreement with that expected from a standard model X with the fitted signal strength of 1.2 plus or minus 0.3 of the standard model expectation. I would like to inject here a personal remark. I take full responsibility of this remark. It is very nice of the standard model X boson to be at that mass. Because at that mass we can measure it at LHC in huge number of final states. So, thanks nature. So, this is our main result. And I would like to mention that these accomplishments are the results of more than 20 years of hard work, extreme dedication, and very talented ingenuity of the Atlas collaboration with the continued support of the funding agency that I would like to thank. But more in general, I think these results are the outcome of the ingenuity, vision, and painstaking work of our community, from accelerator to detector, instrumentation, computing, and physics. I think we all have to be proud of these results, and I hope that they open a door toward a very bright future. Thank you.
Okay, I can only say congratulations also to Atlas, of course.
Thank you. Very kind of you.
Should I say that I'm pleased?
Congratulations.
I think it's obvious.
This is still mine, right?
This is still yours, yes.
As a layman, I would now say, I think we have it. You agree? Yeah. Okay. Okay. Nonetheless, we have agreed that I have one transparency at the end. Just to summarize again. I think we should stress it is a global effort, it was a global effort, and it's a global success. That's number one. The results today are only possible because of the extraordinary performance of the accelerators, including the infrastructure, the experiments, and the grid computing. That was very well presented by both speakers. I think this was key, or is key, to the success. We have a discovery. We should state it. We have a discovery. We have observed a new particle consistent with a Higgs boson. Huh. Which one? That remains open. It's a historic milestone today, but we are only at the beginning. Now a lot of work is ahead of us. It is a milestone. I think we can all be proud, all be happy, but it's at the beginning. And I think also it has global implications for the future, and it comes at the right time, and I think we can be very, very optimistic. Thank you.
Incredible. Thank you. got you. Thanks. Great, huh? I don't think we need too much time. We may not need too much time at all.
No questions, absolutely.
Maybe one more round of applause to all the guys supported the whole project for more than 25 years here. All of them, okay? Okay, I have the impression you're all happy. I don't think we can have too many questions because we are running out of time. Let me first see if there is a remark from Melbourne. Is there any applause in Melbourne?
Yes.
Okay, that's what Fabiola calls trigger.
Yes.
Okay, thank you. Any remark from...
This is Ray Volkus. We're very happy to have taken part in this historic event, and we wish everyone all the best.
Good.
Okay, thank you.
Good point. Very good.
As usual, up to the point. I know there are remarks. Which order?
I take it. Thank you. As a President of the Third Council and on behalf of all the Member State Council delegates, I would like to thank the two speakers, two spokespersons, for their historical presentations. I would like to thank also the third management, the present and the former management, third management, the machine people for the extraordinary achievements, more generally the third staff and the collaborations for their splendid achievements. It is, to my mind, an historical day, as it was mentioned, both for CERN, for particle physics, for the advance of science and of basic knowledge. If I may say so, it is another giant leap for mankind.
It is. I agree.
On behalf of the CERN Scientific Policy Committee, I would like to express the warmest congratulations to the Atlas and CMS collaborations, to the present and past CERN managements that have been making the long history of the LHC, to all the teams involved in the conception, design, construction, and operation of the machine, the two detectors, and the computing infrastructure. The observation of a new particle consistent with the Higgs boson of the Standard Model is a great triumph for science. Particle physicists, both theorists and experimentalists, have been patiently preparing for this discovery for decades. This is just the start of a major program of work for the years to come, whose direction is now clearer. We should find out whether this particle has indeed the properties expected of the Standard Model scalar, and whether it is accompanied or not by additional new particles, which may play a role in the complete picture of electroweak symmetry breaking. This is not the end of the LHC discoveries. Let's be confident that it's just the beginning.
Excellent. Is there any urgent question or remark from the auditorium? Is there any urgent question or remark from Melbourne?
Do I see any hands? I don't see any hands.
Yeah, people want to go to the reception.
Sir Chris. No, wait. Sir Chris holding. Chris wants to say something.
Yeah, Chris.
Well, that's Lynn who asked me to say something. I really would like to congratulate the teams on these fantastic results. Rolf just said 25 years. Actually, it's over 28 years since I gave a 1-hour speech about the case for the LHC after the first workshop in Lausanne in March of 1984. And I think the big surprises to me have been, first of all, that it's taken 28 years, I'm afraid. I certainly hoped it would be quicker than that. But secondly, the magnificent performance of the machine. And I think we really have Lynn to thank tremendously for that. Lynn always said to me, there's this tune shift limit, but we're going to go above it. It's not going to be right because we've got more stable power supplies, and they've done it. Unbelievable. The experiments, I really am amazed that you can use these luminosities. I remember in the 80s, thinking 10 to the 33 almost, that's probably impossible. And it's a lot of hype that we can do these things. But it's worked, and I think to the detector development community and everybody in the two collaborations, we owe a tremendous great debt of gratitude. And finally, to the computing around the world that's been mentioned. And I think below all this, the CERN staff. Not just the scientists, the engineers, the whole CERN staff who have made this possible. It's a great day.
Okay, I fully agree with you. Concerning the 25-28, I was taking the tree level. You took the loop correction into it. No, but I can only join in with concerning the staff, but I don't want to forget that's a global effort, that there are also people from the outside who were helping.
Absolutely.
Lynn, you?
Well, I think you've both been very gracious about the LHC. We appreciate it very much. It is a beautiful machine. But I think that you have built the most incredible scientific instruments, from all the way from the hardware to the data analysis, in global collaboration, and I think you should all be very proud. Thank you.
Okay, finally I would like to ask if one of our four eminent theorists would like to say something. The four eminent theorists who were involved in the early days of the, what is it called, electroweak symmetry breaking?
That's Peter.
Peter is there.
Yeah, you got Peter. Peter's there. Peter!
Yeah, but I didn't want to single him out. It seems yes.
Together.
We are running out of time, gentlemen.
Well, of course, I am only extraordinarily impressed by what you have done. That we have somehow started the whole thing, in a sense, is of course a great pride of us. But really, in part of what you have done, I am just amazed.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
Not only in your lifetime, Peter.
No, not only in your laughter. But I want just to say one thing about your lifetime is the sorrow that my lifelong collaborator and friend Robert Brown could not assist to this extraordinary presentation.
I agree. We have more theorists here, please.
I would like to say congratulations to all of you. This is magnificent. It is a real achievement, and it's wonderful to be at a physics event where there is applause like there is at a football game. Congratulations to everyone.
Clearly, theorists and experimentalists are as one in joining together to applaud this wonderful event which has been presented to us. The machine is wonderful. I've never seen it before, and I'm just overwhelmed by the quality of the machine and the quality of the analysis and the labor, intense labor, which has gone into getting this result. I'm just overwhelmed.
Thank you. Okay, thanks to everybody. The press conference will start now. It will be transmitted into this auditorium for those of you who still have stamina to sit here. We have to go there. I think, as everybody said, it was a memorable event. It was a historic event. And I think we all of us, and all of the people outside watching it in the different meeting rooms in Melbourne, everybody who was involved and is involved in the project, can be proud of this day. Okay, enjoy it. Thank you.